Okay, we're back. We're going to talk about cables loaded under their own weight or with a loading function which is a function of the distance along the cable. The loading function is a function of the distance along the cable. Kind of like we calculated the total length of the cable previously, not a function of x, a function of s. And we replace w of x with w of s. We get very similar equations. T sine theta here would be the integral of w of s ds. For similar reasoning to before, dy dx is the tangent of theta, equals 1 over f sub h w of s ds. And then converting ds dx is over here. Here's dy dx, which is this given by this, and so we can write this, and then we can solve for dx, so we get x is the integral ds over this square root. Go look it up in a table of integrals. This is the solution right here for the case where w equals w naught equals a constant. We're looking at constant force. Now this is a cable under its own weight. Let's say you have a distance x here. There's going to be more weight. This cable is longer in this section. There's going to be more weight right here than in the middle. We can take the same width, but this is a shorter piece of cable from here to here. So there's going to be more weight here than over here. And that's the point of this analysis, hanging under its own weight. Previously, it was like a cable stay bridge. You have a load, the cable is supporting some kind of load underneath it, which is constant with respect to x. This time, the weight is constant with respect to s. And this is important for like power lines, for aluminum lines running between high tension cables, electricity, and so forth. Anytime you need to run a cable between 2 points, will it break under its own weight? That's kind of the question to ask. So you noticed up here, we went into hyperbolic sines. This is the inverse hyperbolic sine. And take a look at Wikipedia for hyperbolic functions. This is what they look like. The hyperbolic cosine in blue, the hyperbolic sine in orange, the inverse functions also plotted. The hyperbolic cosine cannot be less than 1. Here's a few properties, but go to Wikipedia for a lot more. This is how they're defined, hyperbolic sine and cosine. The hyperbolic sine squared plus the hyperbolic cosine squared is the hyperbolic cosine of 2 times the argument. So this is starting to look like trig functions, similar to trig functions. Regular trig functions, if you add the squares of the 2, you get 1. Well, in this case, when you subtract the squares of the 2, you get 1. And here's a double angle formula, or double the argument. It's hard to call it an angle. Okay, so we have this situation, cable under its own weight, 20 meters, 6 meter, h is 6 meters, and W naught is 5 newtons per meter. So we do this integral. And we get this, anyway, this expression here. Just like looking it up in the table of integrals. Now, the trick is finding these constants right here. So dy dx equals this, and that's from previously. We found that out. Well, at s equals 0, it tells us this right here. Dy dx equals 0 at s equals 0, which makes C1 equals 0. So that simplifies the equation. And oh, it's hard to see the equation right way down at the bottom. dy dx equals W naught S over FH. Just this equation right here. Okay. And when S equals 0, X also has to equal 0. So we notice the second constant of integration, where's X? There it is. X has to equal 0 when S equals 0. The hyperbolic sine, inverse sine, and the hyperbolic sine of 0 is 0, which forces C2 to equal 0. So we get this expression for S. A lot of times, because of symmetries of the situations, the integration constants can be found pretty easily like this. Substitute it into the equation for dy dx. So let's go back. Where is dy dx? There we go. W naught S over FH. Well, now we have, anyway. The integral of the sine, hyperbolic sine, is the hyperbolic cosine. So that makes it particularly easy. We can integrate that. We get a third constant of integration now. At y equals 0, x equals 0. The cosine, the hyperbolic cosine of 0 is 1. So C3 has to be negative FH over W, and just rewriting it. Oh, there it is. It's written right down here. And just rewriting it, we can express y this way. At L over 2, when x equals L over 2, we get H. And then finally, so we can write down this equation at we can substitute in L over 2 and all these substitutions to get this equation in FH. You can't solve this algebraically. You have to do it numerically. And Excel is pretty good at that, so I just want to go show that. Okay. Come on, Excel. Wake up. What I've done is programmed. Excel has this thing called a solver. And what you do is you set up your equation. I did it 6 minus. Okay, let's go back to here. 6 minus this expression right here. 6 minus A1, which is what we're going to vary, divided by 5 kilonewtons. There's the 5 newtons, 5 newtons per meter. Hyperbolic cosine, 50 over A1, 50 over what we're trying to find, minus 1. Okay. And the goal is to set that to 0. So I'm just going to start here. This is my first guess. This is how the solver works. So I go to Data, I go to Solver, the solver tool in Excel. MATLAB can do it also. So I'm going to change B1, this cell that's highlighted right now. So this is the objective. We want to set this to be 0. Because previously I took 6 minus this expression has to equal 0. That's how I wrote the solver. And then by changing the value in A1, let's see, there we go. By changing this value here, and I took the initial guess for A1 to be way off. And then click the solve. And then there's a solving method. You can try different things. Anyway, crunch, 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 crunch. Solver results. Okay, it likes the solution. 45.9. Just like the Hibbeler book said, 45.9. There we go. And then we can make the substitutions for the deflection of the curve, the half length of the cable. We can find that, make all the different substitutions. And now we want to find, similar to the previous, similar to cables under constant loading with the function of x, we want theta to be maximum, which happens at either end. And you just calculate the tangent of theta and you find theta, and then you can find T max. Okay, this is the end of chapter 7. I just wanted to go through some of the equations before we finally wrap up. So when you have a distributed load, dV dx equals W, dm dx equals V. Watch out if the arrows point down, you'll have a negative sign. Minimum or maximum moment happens when the shear equals 0. And then here's the integral forms. So there's that. This is for distributed loads. Summary for point loads. The change in shear is F when you go through the point. And watch out for the reversal of direction if F is up versus down. The change in moment is M naught, as in figure B. These are the equations for cables under a constant load, where the load distribution is a function of x. So here's all the equations you get to work with. I would not worry about the math of deriving all these equations because it is rather complicated. Just understand what they do and how to manipulate them. And a cable under its own weight, the very last thing we did, and you have all these expressions here. See, dy dx, y is a function of probably the last one to find the shape of the curve. I want to make sure I did that with the previous one. Yes, I did. There it is. Quadratic versus hyperbolic cosine. Okay, that is the end of video, end of this portion of the chapter on internal forces. We are going to go on to friction next.